Okay, so what I'm going to do in this video is I'm going to go over the exam number 1 for kinetics. Okay, so in the first question, it says in 2 to 3 sentences, define chemical kinetics. So there are different possible answers for this, but we could say that chemical kinetics is the study of rates of reaction used to determine the rate law of a reaction or reactions, the energetic study of activation energy, sorry, and the mechanisms of chemical reactions. Okay, so that's not written properly as like a 3 sentences, but essentially that's the idea. Okay, so we use chemical kinetics to find rate laws. We use it to study the rates of reaction, how fast they are, but we also use it for activation energy studies as well as mechanisms, determining what the mechanism of the reaction is. Okay. All right, so let's do the second one. In 2 to 3 written sentences, define the rate of reaction. Well, this one probably doesn't even need 2 to 3 sentences. One sentence probably will do, but the rate of a reaction is sometimes called the speed of the reaction. In fact, we'll say speed or velocity of a reaction. And the rate of reaction involves measurement of the changes in concentration of either reactants or products with respect to time. Okay, so it has to do with time measurements, right? We're measuring the changes in concentration over time. In the third one, describe how the average rate and the instantaneous rate are similar and how they are different. Okay, well, the two measures of rate are similar in that they each measure how fast a reaction is proceeding, right? They measure how fast the reaction is, right? They differ, however, on the specifics of how they are measured. In average rates, the rate is measured over a relatively long period of time. In instantaneous rates, the rate is measured at one time, right? It's measured at one time. Okay. All right, let's get rid of the underline there. Okay, so the main difference, oops, sorry, let me respell this. Okay. The main difference is that for instantaneous rates, you're measuring at one specific time. Some people will refer to the tangent line. We can look at it from that perspective, and looking at the average rate as the secant line. But the idea is that for the average rate, we're measuring it over two, essentially over a period of time. So we very often will make two measurements. Okay. All right. So let's take a look at the next one. The next one, we start getting into calculations. Okay. So let's take a look at this one. For this one, the idea is that we want to measure the rate of reaction here. Okay, we want to calculate the rate of reaction for this one. So to calculate the rate of reaction, we just need a change in concentration divided by a change in time. That's all the rate is, right? So the rate is the change. So I'll use a D for change in the concentration of the reactant. So we can use H2 here, for example. So D, sorry, get that bracket right. In fact, let me bring this over a little bit. Oops. There we go. So D concentration of H2 slash dt, right? Change in time. So D is referring to the change in. So the change in the concentration of H2 divided by change in time. So for this one, it's pretty straightforward. The change in concentration is, well, our final concentration is 0.305. So 0.305. The units are in molarity, minus the initial concentration is 0.500. Okay, so let me put that in parentheses just so we can put that in a proper format. Divided by the change in time. So the change in time would be the final time, 15 seconds, minus the initial time, 10 seconds. Okay. All right, so for that one, that would be, 0.305. So you get negative 0.195 molar divided by the change in time is 5 seconds, so 5 seconds. Okay, so then all you need to do is just take 0.195, divide that by 5, and you get 0.039, so negative 0.039, and that'd be molarity per second. Okay, so that would be negative. Now, typically, the rate is a positive value. So really what I just calculated there technically is not the rate. I calculated the change in concentration of H2 divided by the change in time, which is related to the rate. The rate would be the positive of that value. We generally have positive rates of reaction, okay? So all you really need to do at that stage is then say, okay, we're going to change, we're going to change the value to a positive. If you want to look at it this way, you could say it's the absolute value of the change if you want to do it that way. That's another kind of approach to thinking about it, but it should be a positive value. Okay, so that would be our answer right there. Now let's check out to make sure we have the correct number of sig figs. It looks like we're okay because it's actually a little bit ambiguous because if you think about it, we're doing multiplication, division, and subtraction in this, or actually I should say we're doing division, but we're also doing subtraction. So there's actually two rules of sig figs. For the numerator, it's 0.305 minus 0.500. So that should have three significant figures, 3 digits past the decimal point. But in the denominator, there's only 2 significant figures in 15, and 10 seconds is actually ambiguous. It might be 1 significant figure, it might be 2. So generally, we try to put a decimal point if we want that to be 2, but not all questions will have 2. We'll put the decimal point in for whole numbers. So for this one, if you do 2 significant figures, that would certainly be fine. If you do 3 significant figures, that would probably be okay because there is some ambiguity in terms of how many sig figs are in here. For the most part, we would probably try to do 2 sig figs because 15, you're dividing by 15 minus 10. Let's assume that's 2 significant figures. When you do division, you want to use by the smaller number of sig figs, and that would be 2 sig figs. Okay. So 0.039, the 0 is not significant. A leading 0 is never significant. So that means it's not. So the 3 and the 9 are the significant values. So there's that one. Let's move on up to number 5. Consider the graphs above. Is the rate of reaction constant or changing in 2 to 3 sentences? Explain how we know. The answer is changing. The rates of reaction are changing. In fact, you can figure out how fast the reaction is proceeding from either the reactant or the product. So the reactant is decaying away, the product is being formed, it's increasing over time. But the main issue here is whether the curve is straight or not. If it is a curve, if there is not a constant slope, that means the rate is changing. And we see that in most chemical reactions, that the reactant decays away very rapidly at the beginning and then very slowly toward the end there. So that rate of reaction is changing. In order for this to be a constant rate, the rate of reaction would essentially have to go down by like a straight line. If it was a straight line decreasing, or for the product a straight line increasing, that would be a constant rate. So for this one, we would say the rate of reaction is changing. So we'll state that, then we'll say why. We know this because the curves are nonlinear. For a reaction rate to be constant, the decay or increase in product concentration must be linear. Okay. So it doesn't mean that the reactants don't decrease. Decreasing doesn't mean anything about whether it's a constant or not, the rate. Reactants should react, so they should always decrease. It's the shape of the curve that's important. Okay. So number 6, consider the equation. That's an equation, right? It's a mathematical equation. R equals K times the concentration of A to the X times the concentration of B to the Y. Those are presumably reactants. What's it called? Well, that type of equation is called a rate law. Now, if you want to be technical about it, we can actually call it a differential rate law. And then, and that differentiates it from the integrated rate law. What is the symbol K called? Well, that's called the rate constant. Okay, that's pretty straightforward. Number 7, consider the following data set and the chemical equation. So here's the chemical equation here. And notice they give you a sort of a generic expression for the rate law. R equals K times the concentration of H plus to the X times concentration of OH minus hydroxide to the Y. They give you several different combinations of concentrations and initial rates, and then ask you to figure out X, Y, and K, the rate constant, right? Okay. So what you can do is you can find 2 of these data sets, 2 of these rows, where one of the reactants is changing concentration, but the other one is not. So it could be the second one divided by the first. And we're going to use this rate law for each of those. So what I'm going to do is I'll say R2. So let's make this the second, and we'll make this one the first, and this will be the third. So R2 divided by R1 would be, and then what you do is you put in the expressions. So K, and then for the concentration of H plus, it'd be 0.400. And that would be raised to the X. Okay, and then I'll superscript that in a little bit. And then times 0.050 to the Y. Okay, and then I'm going to divide that by, so let's do it this way. I'll just underline this. There we go. And then we'll do K. And then we're going to do experiment 1, which is 0.200 and 0.050. 0.200, and that would be to the X. And then 0.050 to the Y. Okay. And then I'll just go ahead and superscript these. Probably should, oops. Let's superscript this. Okay, so there's our values right there. Now notice that some of this is going to cancel out. The k's are going to cancel out. K divided by k is 1. And the 0.050 to the y divided by 0.050 to the y is going to cancel. All right, so now we can say then that R2 over R1 would just be 0.4. In fact, let me do it this way. 0.400 to the x. Okay, divided by 0.20 to the x. Okay, and then that can be simplified. That can be simplified, R2 over R1, to 0.400 divided by 0.200, and that's going to be raised to the x. And so that essentially comes out to 2 to the x. Okay, now let me go ahead and superscript these x's. Those are exponents, right? Okay, so that's 2 to the x. Now you come back and you do the same thing. R2 is 0.4 molarity per second divided by 0.2 molarity per second. So you take the ratio of the rates. So 0.40 divided by 0.20, which is equal to 2. And then we just use inspection. We say, look, the ratio of those two rates is 2 to the x, and it's equal to 2. So that means that 2 to the x equals 2, right? Okay, well, just plug in different values of x. X can be 0 or 1 or 2. So if we put in 0, that doesn't work because 2 to the 0 is 1. We put in a 1, that does work. If x is equal to 1, then 2 to the 1 is 2. So that's the case that matches, right? 2, if x were 2, that'd be 4. 2 squared is 4. So that means that x is equal to 1. Yeah, capitalized it there, but that's fine. Okay, so that gives us x. And we do the same thing for y. Now we want to find two experiments where the hydroxide is changing, but the hydrogen ion is not changing, H plus. So the experiments where hydroxide is changing, but H plus is not, is 1 and 3, right? So there's 1, and then there's 3. So for experiment 3, the hydroxide changed. So I'll just do R3 over R1 and do exactly the same thing that we just did before. So R3 divided by R1. And same thing, you're just going to put in K and then, whatever the concentrations are. So 0.200 to the X times 0.100 to the Y. And then I guess I'll just, again, same thing, I'll just go ahead and underline that. So we can do ratio, and then K, and then for experiment 1, so we're doing 3 over 1, 0.200 to the X, 0.050 to the Y, okay? And so I'll superscript it in a moment, but what happens is the K cancels, the 0.200 to the X cancels, and then you get R3 over R1 equals 0.100 to the Y divided by 0.050 to the Y. And just so I can put this all on one line, that would be, 0.100 over 0.050 to the Y, which is 2 to the Y. Okay, so now we got 2 to the Y. So the ratio of R3 to R1 is 2 to the Y. Okay, so let me go ahead and superscript it. Okay, so remember, these are all exponents. X and Y are the exponents. We already know that X is equal to 1. Now we're figuring out what Y is. It turns out Y is going to end up being 1 also. In order for it to be anything other than Y, the math would have to be a little bit different. Okay, so there we go. So looks like we got all that exponents up there, right? Okay. So now we do the same thing with the initial rates. We're going to take 3 over 1. So 0.40 divided by 0.20. So then R3 over R1 is also 0.40 divided by 0.20. Is that right? Yep. 0.40 over 0.20. Okay, that's equal to 2. So that means that R3 over R1 is equal to 2 to the Y, but it's also equal to 2. So that means 2 to the Y equals 2. So we'll come over here and I'll just say 2 equals 2 to the Y. All right. So from that, we can see that the only solution that works for that is that Y has got to be equal to 1. If it said 4 equals 2 to the Y, then Y would be 2. But it works out. So Y equals 1. So now we're almost there. Now we know the rate is equal to K times the concentration of H plus to the 1. So I just won't even put an exponent times the concentration of hydroxide to the 1, and I won't put anything in there. Okay. Now we've got to figure out what K is. So what you do is you take this equation right here, the rate law, and you solve for K. You divide both sides by H plus concentration, and you divide by hydroxide concentration, and that'll give you K. I know this it's capitalizing it, but we'll fix that. R divided by concentration of H plus divided by concentration of OH minus. Okay, there we go. That looks better. And then again, let's be careful because capital K is what's called the equilibrium constant. And I'll try to make this a small r. Okay. All right. So now all you got to do is just pick one of the experiments. You could do all 3 or you could just do one. I'm just going to do one. So I'm going to take R 0.20. Okay. So 0.20 molarity per second, right? That's the units of the rate. And yes, this is often referred to as the method of initial rates, if you're wondering that. Okay, then we're going to divide that by the concentrations. I'm doing experiment 1, so 0.200, 0.05. Molarity, and then 0.050 molar. Okay, so let me just make sure that we see that, in fact, what I'll do is I'll put this in like a different kind of bracket to point that we're taking the 0.20 molarity per second, the rate, divided by both of these, right? Both of those concentrations. Okay, so I'm going to take that 0.20, divide that by 0.200, divide that by 0.05. It looks like I get about 20, so 20. Now, what about the units? Okay, significant figures is an issue here again. Again, I'm using these sort of round numbers, and there's ambiguity in here. And so actually, there's no ambiguity here. These are 3 significant figures, but these ones are only 2. So probably you're going to do 2 significant figures. So 20. So if you want to be on the careful side, you just put a point there, 20 point, and that's 2 sig figs. Okay. So now the units would be molarity per second divided by molarity. So one of the molarities in the denominator cancels with the molarity in the numerator, but you still have another molarity in the denominator. So m to the -1 times seconds to the -1. Okay, so then those would be superscripted. There we go. There's our answer right there. So 20 point reciprocal molar reciprocal seconds. Okay. And that would be our answer there. Okay, let's take a look at number 8. Number 8 is convert this number to scientific notation. Okay, well, you move the decimal point 1, 2, 3 places to the right. So it would be 1.351. We moved it 3 places. So times 10 to the minus 3. Okay. Remember, we want to get a number between 1 and 10. So 1.351 is a number between 1 and 10. And let's go ahead and underline that. There we go. Okay, so up to number 9. Now, number 9, we're assuming it's a first order kinetics. So the reaction is N2O4 turning into 2NO2. It's first order. So the equation here is for the first order time-dependent kinetics. Use the following equation and the data provided to find the missing number. The missing number is the concentration of N2O4 at the time equals 10 seconds. We're given the rate constant of 500 reciprocal seconds, which is a huge number. Most likely the concentration of N2O4 is going to be very close to 0, because what's going to happen is when you take minus KT and ln of 0.25, you're going to get a very large negative number. And a very large negative number, when you take the anti-log of that, you get essentially 0. It's kind of like, ln of x equals minus 1,000 or 100, x is going to be essentially 0, very close. We might be able to get a value out of the calculator, just sort of depends. Okay, so I'm just going to substitute in the numbers. So I'm going to say, hey, let's take this. I'm going to paste it over here. And we have our values of KT right there. So K is 500. So 500, I'll leave the units out. T is 10 seconds. Okay. And then we're going to take the natural log of 0.25. Okay. All right. So I'm going to do, what I'll do is I'll just take everything on the right side. So 500 times 10 is 5,000, right? It's going to be like okay, so let me put in here minus 5,000 plus ln of 0.2. In fact, let me just go ahead and do that. ln of 0.25. So ln 0.25 is negative 1.386. So two negative numbers, you add them together. So that's minus 5,001.386. Okay, whoops. 5,001, which, to be honest with you, is approximately equal to minus 5,000. It's not going to be any different, to be honest with you. Let me just put this in here. There we go. You'll get the same value. You can put in either one. So now to get N2O4, to get the concentration of N2O4, we have to do the anti-log. We have to get rid of the ln. So I'm going to come over here. So it's going to be, E2 raised to this number right here. That gets rid of the ln. There we go. And again, if you want to put negative 5,001.386, you can do that too. You're going to get essentially the 0. You're going to get a 0, really, is what's going to happen. Okay, so E raised to that. So let me just put this up as an exponent. Okay, so if you take that number, negative 5,001.386, and you do the anti-log, e to the x. Oops, I'm sorry, I had to do the anti-log first on this calculator. So minus 5,001.386. This calculator gives you 0. Most calculators are going to give you 0. Okay? Now, technically speaking, it's not 0. It's just your calculator is incapable of being able to do this calculation because it's such a small value that it can't do that many significant figures on it. But that's okay. Oops, sorry. 0.00, and then that's molar. That's your concentration. So it's very dependent on the values. So if K had been 0.5 instead of 500, that would change the answer. Now you'd get a concentration that would be a value your calculator could get. Had I made it 1 second and made the value of K 0.5, then again, you'd get a concentration you would calculate there, okay? But the point is that you go to the calculator, you do this last step, and this is such a small number, e to the negative 5,000 is essentially 0, okay? All right, so there you go. So that pretty much touches on the first three sections. This exam doesn't cover section 4 or 5, which is okay. There's a lot in sections 1, 2, 3 anyways, okay? So what you want to do is you want to kind of go over this exam again, try it again for yourself. I have to spell this properly. I will post this as well. So we post it as a document and practice it so that you can really kind of get the material down that you didn't get right. Hopefully all of these kind of calculations and definitions and such make sense to you now. Okay, so take care.